In this lesson 8.4, we will learn about electric power and resistors. Lesson 8.4 has the following goals: to define electric power, resistor, and describe the electric power equation and explain how to read resistor color code. Goal number 2, to calculate electric power in circuits of resistors in series, parallel, and complex arrangements. Electric power. Power is associated by many people with electricity. Every day, we use electric power to run our modern appliances. Electric power transmission lines are visible examples of electricity providing power. We also use electric power to start our cars, to run our computers, or to light our homes. Power is the rate at which energy of any type is transferred. Electric power is the rate at which electric energy is transferred in a circuit. To get started, let's think of light bulbs, which are often characterized in terms of their power ratings in watts. Let us compare a 25-watt bulb with a 60-watt bulb. See figures A and B at the right. Although both operate at the same voltage, the 60-watt bulb emits more light intensity than the 25-watt bulb. This tells us that something other than voltage determines the power output of an electric circuit. Incandescent light bulbs, such as the two shown, are essentially resistors that heat up when current flows through them. They get so hot that they emit visible and invisible light. Thus, the two light bulbs in the photo can be considered as two different resistors. In a simple circuit, such as a light bulb with voltage applied to it, the resistance determines the current by Ohm's law, so we can see that current as well as voltage must determine the power. Calculating electric power. The concept of power was introduced in Lesson 4.2.4, or work and power. Basically, it is a measure of how rapidly a standard amount of work is done. In electric circuits, the power is a function of both voltage and current. By this equation, P equals I times V, where P is the power in watts, I is the current, V is the voltage in volts. Since V equals IR and I equals V over R, power can also be written as P equals I squared times R, or P equals V squared over R. Depending on the given situation, we can either use equation 1 or equation 2 or equation 3 to solve for the electric power. Let us do some examples now. A typical older incandescent light bulb was 60 watts. Assuming that 120 volts is applied across the light bulb, what is the current through the light bulb? Solution. Here we are given the power, which is 60 watts. Voltage is 120 volts, and we are required to find the current I. So, we use the formula P equals I times V, rearrange to solve for I, and substituting the values, we get I equals P over V, or 60 over 120 equals 0.5 amp. Example number 2. An electric space heater is connected across a 120 volt outlet. The heater dissipates 1,320 watts of power in the form of electromagnetic radiation and heat. Calculate the resistance of the heater. Solution. We are given the power which is 1320 watts. The voltage is 120 volts and we are required to find the resistance R. So, we use this formula P equals V squared over R. Rearrange to solve for R and substituting the values we get R equals V squared over P or 120 squared divided by 1320 equals 10.9 ohms. Example number 3. Each resistor in the circuit below is 30 ohms. What power is dissipated by the battery? We see that R1 and R2 are in parallel, and the parallel connection is in series with R4. Solving for the equivalent resistance for R1, R2, and R4, we get R124 equals 1 all over 1 over R1 plus 1 over R2 plus R4. Substituting the values, R124 equals 46.67 ohms. For resistors 3 and 5, which are connected in series, the equivalent resistance is R35, which is R3 plus R5 or 30 plus 30 equals 60 ohms. The new circuit diagram can be drawn as in the figure below. So, solving for the equivalent resistance of the whole circuit, all of these resistances now are connected in parallel, so the total resistance is 1 all over 1 over 1 R124 plus 1 over R35 plus 1 over R6 equals, substituting the values, the total resistance is 14.29 ohms. Thus, from the formula P equals V squared over R, substituting the values, we get P equals 12 squared divided by 14.29 equals 10.08 watts. Example number 4. A calculator is rated at 0.10 watt and has an internal resistance of 22 ohms. What battery potential difference is required for this device? Here we are given the power, which is 0.10 watt. The total resistance is 22 ohms and we are required to find the voltage. So, using the formula P equals V squared over R, rearrange to solve for V and substituting the values, we get V equals square root of P times R, or substituting the values, we get V equals 1.48 volts. Let's look at the resistors now. What are resistors? Resistor is a device which opposes or resists the flow of current through it. The property of a resistor through which it opposes the flow of current is called resistance. The unit of resistance is ohm. Resistance is directly proportional to the resistivity of the material and the length, whereas it is inversely proportional to the area of the resistor. The resistors are available in various sizes and shapes. The resistors are classified on the basis of the following characteristics: the power rating, the tolerance, the temperature coefficient, the noise, the frequency response, and the stability. The types of resistors. Resistors can be classified into the following two categories: fixed resistors and variable resistors. Fixed resistors have a fixed value throughout their lifetime. That is, once fabricated, the value of resistance of these resistors get fixed. The following are examples of fixed resistors. Carbon composition resistors. The carbon composition resistor are of cylindrical type. The resistive element of this resistor is made up of either carbon powder or graphite powder mixed with ceramic clay. The resistor has two attached metal caps and two wires coming out of its two ends. The resistor is covered up with plastic coating which is made up of carbon. They were generally used to withstand high energy pulses, but they have become obsolete now because they have poor temperature coefficient and poor stability. They produce more noise and have less accuracy. They are now replaced by the film type resistors. Applications are in protection of circuits, high voltage power supplies, current limiting, strobe lighting, and welding. Number two is carbon film resistors. The carbon film resistor is made by depositing a thin layer of carbon film on the ceramic substrate. The carbon film is deposited in the form of a helix. By changing the pitch of the helix, the resistance of the carbon film resistor can be changed. The carbon film resistors are low-cost resistors, and they also produce less noise as compared to the carbon composition resistor. The tolerance value of these resistors is less than the carbon composition resistors. These types of resistors are used in high voltage and high temperature resistance. These resistors are available in wide range of values. The applications are in high voltage power supply, radar, X-ray, and laser. The third example of fixed resistors is the metal film resistors. As far as the construction is concerned, the metal film resistors are very similar to the carbon film resistors. They are made by depositing a film of metal on the ceramic substrate. These types of resistors are low-cost resistors. They also produce less noise as compared to the carbon composition resistors. They have high stability and low temperature coefficient. They are generally preferred for high-frequency applications. So the applications should be in active filters and bridge circuits. The fourth example of fixed resistor is the metal oxide film resistor. In terms of construction, they are quite similar to the metal film and carbon film resistors. But here, instead of metal or carbon, the metal oxide film is deposited on the ceramic substrate. Tin oxide is generally used as the metal oxide film. They are also low-cost resistors. They produce more noise, are unstable, and have low tolerance as compared to the metal film resistors. They are, however, better than the carbon film resistors in terms of noise production, stability, and tolerance. They have poor temperature coefficient as compared to the metal film resistors. However, they are still used mostly in high temperature applications. The fifth example of fixed resistor is the wire wound resistors. They are used quite frequently. The construction of the wire-wound resistor is such that the metallic resistive wire is wound over the ceramic material. The resistance of the wire-wound resistors depends upon the thickness of the metallic wire. Metal alloys of copper or silver are used as the winding material. The benefits of this type of resistors are that they provide very high accuracy. They also have very low temperature coefficient of resistance. Because of this low temperature coefficient of resistance, they are highly suitable for high precision applications as well as for the high power applications. However, it is to be remembered that these types of resistors are not suitable for high frequency applications. They are applied in stereo systems and high power applications like transducers and televisions. The sixth example of a fixed resistor is the surface mount resistor. The surface mount resistors are very tiny and they are generally employed in the motherboards. The composition of the surface mount resistors is such that a thin layer of resistive film is deposited on the ceramic body of the resistor. Generally, metal or oxidized metal film is used as the resistive film. On the top face of this resistor, a thin insulating layer is deposited. Metallic contacts are situated at the both sides of the surface mount resistors. These are present so that the resistors can be soldered on the PCB. As the surface mount resistors are made up of the metallic film or metal oxide film, very high accuracy and very low tolerance value can be achieved. Now, the variable resistors. The resistor whose value can be changed is called variable resistor. These resistors can take any value between zeros to a certain maximum value. They are generally used in electric circuits to adjust the value of voltage and current. These resistors can be classified into the following three categories. 1. Potentiometer resistors. It is a device used to measure the EMF by balancing it against the potential difference. The potentiometer is further divided into two types, the carbon potentiometer and the wire-wound potentiometer. The second type of variable resistor is the rheostat resistors. This is a resistance wire on an open tube of ceramic covered with a covering of vitreous enamel. The third type of variable resistor is the trimmer resistor. Trimmer is a device to adjust the resistance, and the resistance need not be compulsory variable. The trimmer can be adjusted with the help of a skew. Now the resistor color codes. The resistance value, tolerance, and wattage rating are generally printed onto the body of the resistor as numbers or letters when the resistor's body is big enough to read the print, such as large power resistors. But when the resistor is small, such as 1/4 watt carbon or film type, these specifications must be shown in some other manner as the print would be too small to read. So, to overcome this, small resistors use colored painted bands to indicate both the resistive value and their tolerance, with the physical size of the resistor indicating its wattage rating. These colored painted bands produce a system of identification generally known as a resistor's color code. Calculating resistor values. There can be anywhere from 3 to 6 colored bands as in figures A to D on the body of a resistor, with 4 bands being the most common variation. The first few bands always represent digits in the value of resistance. Then you will find a multiplier band to signify moving the decimal right or left. The last bands represent tolerance and the temperature coefficient. The resistor color code system is all well and good, but we need to understand how to apply it in order to get the correct value of the resistor. The left hand or the most significant colored band is the band which is nearest to a connecting lead, with the color-coded bands being read from left to right as follows: digit, digit, multiplier equals color, color times 10 to the color in ohms. The picture at the left shows the numerical value for each of the color in the 4-band, 5-band, and 6-band color code system. 3 or 4-band resistors. The first 2 bands always denote the first 2 digits of the resistance value in ohms. On a 3 or 4-band resistor, the third band represents the multiplier. This multiplier will basically shift your decimal place around to change your value from mega ohms to milliohms and anywhere in between. The fourth color band signifies tolerance. Keep in mind that if this band is absent and you are looking at the 3-band resistor, the default tolerance is 20 plus or minus 20%. Let us do some examples now. Example number 1. Let us determine the value of the first resistor in the figure at the left. Reading from left to right, we have first band color is yellow. The value of the first digit is 4. Second band color is violet. The value of the second digit is 7. Third band color is red. So the multiplier is times 100. Fourth band color is silver. The value of tolerance is plus minus 10%. Therefore, the final answer is 4700 ohms plus minus 10% or 4.7 kilo ohms plus minus 10%. The 5 or 6 band resistors. Resistors with high precision have an extra color band to indicate a third significant digit. If your resistor has 5 or 6 color bands, the third band becomes this additional digit along with bands 1 and 2. Everything else shifts to the right, making the fourth color band the multiplier and the fifth band the tolerance. A 6-band resistor is basically a 5-band type with an additional ring indicating the reliability or the temperature coefficient in parts per million per Kelvin specification. Using brown, the most common 6th-band color, as an example, every temperature change of 10 degrees Celsius changes the resistance value by 0.1%. Example number 2. Let us determine the value of the second resistor in the figure at the left. Reading from left to right, we have First band color is blue, so the first digit is 6. Second band color is gray, so the value of the second digit is 8. Third band color is black, so the value of the third digit is 0. The fourth band color is red, so the multiplier is times 100. And the last band color is gold, so the tolerance is plus minus 5%. Final answer is 680 times 100 ohms plus minus 5% or 68 kilo ohms plus minus 10%. Let us convert resistance value into color code. We now know how to read a resistor's color code to determine its resistance value. Let us reverse the process and determine how to convert a resistance value into its proper color code sequence. The first step in this process is to completely write out the number, replacing any metric prefixes with the proper number of zeros. Break the number into first digit, second digit, then count and record the number of zeros assigned the appropriate color for the recorded digits. Example number 3. Convert to color codes 1.5 kilo ohms plus minus 0.1%. Solution. The first step in this process is to completely write out the number, replacing any metric prefixes with the proper number of zeros. So, 1.5 kilo ohms plus minus 0.1% is the same as 1.5 times 100 plus minus 0.1%. First digit 1 is brown. The second digit 5 is green. The multiplier times 100 is red. And the tolerance 0.1% is violet. Therefore, we have a 4-band resistor, first brown, then green, then red, and finally violet. Example number 4. When a resistor labeled brown, black, brown is connected to 120 volts, what will be the current in the circuit in amperes? Solution. Brown, black, brown. The resistance is, for brown, it is 1. For black, it is 0, second digit. And the multiplier brown is times 10. Therefore, we have 10 times 10 is just 100 ohms. Using Ohm's law, the current is V over R. Therefore, substituting the values, 120 divided by 100 equals 1.2 amperes. Example number 5. When 220 volts produce 0.22 ampere of current, what will be the label in the resistor? Solution. First, we solve for R using Ohm's law. R equals V over I. So, substituting, we have 220 over 0.22 amperes equals 1,000 ohms. So, writing out this 1,000 ohms, we have 1, 0, and then times 100. 1 is brown, 0 is black, and times 100 is red. Therefore, we have this resistor, we have brown, black, and red. Thanks for watching. Please do not forget to subscribe.